Hi everybody, welcome to this course on applied statistics. Today we shall discuss descriptive statistics and I shall give you practical examples with some sample code from R programming language. So assume that you've installed R and RStudio on your computers and are ready to use them. If not, please take your time to do just that. Descriptive statistics is also called exploratory data analysis, and it is used for exploring the datasets to understand its properties that then direct further analysis. This can involve many steps, but broadly these steps are visualizing the distribution of data elements, measuring the central tendency, and measuring the dispersion or spread of data. We shall discuss each of these topics in detail today. But before we discuss those details, first a word of caution. Before we start any kind of data analysis, we must ensure that data is ready for this analysis. If that is not the case, we must clean or pre-process the data. Cleaning can mean any number of things, but a few examples are listed here. First is missing data. Some parts of data can be missing. This can affect the analysis. For example, reporting the average height of class while many heights are missing can produce erroneous estimates. Statistical and machine learning methods provide various ways of dealing with missing data that you must look up as self-study. Misspelled data must be corrected. Likewise, impossible data must be corrected. For example, a month cannot be numbered greater than 12. Likewise, a day's value cannot be greater than 31. Outliers can impact data analysis. Informally, outliers are extraordinary values. For example, when analyzing the daily number of customers entering a store, if one day the number skyrockets, you must question if this spike is due to a recording error and hence must be omitted from the analysis, or if it represents a seasonal pattern that must be included in the analysis. Another thing that can affect our analysis is the type of data we are analyzing. Discrete data that takes exact values such as integer values or a finite number of values such as a fixed number of categories can sometimes be treated differently from continuous data such as real numbers. Therefore, understanding your data is one of the first steps in data analysis. Let us now start exploring data. Whenever possible, visualize your data. And one of the most popular visualization of continuous data is called frequency distribution or the histogram. To construct a histogram, the first step is to bin or bucket the range of values, that is, divide the entire range of values into a series of intervals, and then count how many values fall into each interval and plot that along the y-axis. The bins are usually specified as consecutive, non-overlapping intervals of a variable. The figure on your screen now shows an example of binning for some real value data and the corresponding data. You can clearly see why binning is needed, because without binning, real value data may contain all unique values, and so their counts will always be 1. Without binning, we shall not see the clustering effect that we can currently see here in this figure. The picture that a histogram paints is what in statistics we call a distribution of data. Now, frequently, the distribution looks like what we call a normal distribution or a Gaussian distribution, as is in the case with the picture at the bottom of your slides. Now, an ideal normal distribution is represented by the black curve that goes around the blue blocks in the bottom picture. So we can say that the actual distribution approximates a normal distribution. Approximations to normal distributions are common, but it's not always the case. Now, if instead we have categorical data, then what do? For example, we want to plot how many different models of cars we have. and then each model represents a category of data. In such instances, we use bar charts as shown in the figure. Note it is conventional to leave some gaps between the bars. Also note, changing the order of the categories here does not really change anything, even though visually it might look different. Now, in contrast, in a histogram, there is always a logical order on the x-axis. So at this stage, I'll leave you with a question to think about and discuss with your fellow learners. I must stress that discussion with the fellow learners is a great way of learning instead of just thinking individually all the time by yourself. So the question is, for integer data like car prices, will it be better to use bar charts where each price is counted separately, or a histogram where a range of prices are counted? So pause and think and comment under the video. In the meantime, let me get back to histograms and show you some R code. Let us read in data from a sample file now called usedcars.csv. The link to this data set is in the description beneath this video on YouTube. So we use this function read.csv available in R. As the function reads in the .csv file, we store the results in a variable called usedcars. Note you must not type the greater than symbol at the start. This greater than symbol or the angle bracket is called the R prompt, and R automatically presents it to you to show where to type in your code. We then view this data set with the view function in R, and we can see that the used cars is stored in a tabular structure with multiple columns. Let us focus at the first column called year and draw its histogram. But before drawing, we can use another very useful function called table to see all the unique values in the year column and their respective counts. Next, we use the hist function to plot the information that the table function just printed out. As you can see, this distribution is not like the normal distribution. Instead, most of the scores, that is counts of years, are bunched towards the higher end. In addition to viewing the data set as shown here, R provides a very useful function called str that prints out the structure of the data set. So if you see that it prints out the data type of each variable, for example, year is an integer variable, whereas model is a factor variable. You might say, well, model must be a character string. You're right, but the reason it is showing up as a factor is because read.csv function automatically converts character strings into factor variables. If you do not wish to do that, use read.csv as I show now on your screens. You must self-study what factor variables are and when you should use them. A typical histogram looks like a bunch of rectangular bars as shown in this chart here. As the number of bars increases, the top of the histogram increasingly starts looking like a frequency curve. Alternatively, if you consider the midpoints of the bar tops, so for instance, if you go to the chart on the left side and you see various rectangular bars there, so note the midpoints of the top of each bar. And then if you connect them with a smooth or freehand curve, you also get what is called a frequency curve. Let us now discuss the properties of distribution, and the first such property is skewness. So far we have seen distributions that are symmetric. That is, if we cut the distribution in half, the two halves look like mirror images of each other around the midpoint. Such a distribution is called such a distribution, such as the normal distribution, is said to have no skew. However, many times this is not the case. For example, if the distribution is bunched to left, we can see a tail appearing to the right. This is called a right skewed distribution with a positive skew. Likewise, the distribution is bunched. If the distribution is bunched to right, we can see a tail appearing to the left. This is called a left skewed distribution with a negative skew. We can now also compute the skew in R. To do that, we must ensure that a package called E1071 is installed and loaded. If it has been installed already, you can load a package using a function called library as shown here. Thereafter, you can call the function skewness on your data. For example, the mileage data has a positive skew value, whereas the year data has a negative skew value. The next property we discuss is called the mode. It is also a measure of central tendency, that is, where the majority of distribution tends to be grouped around. Note, we use multiple properties to get the central tendency, and mode is the first such property. The mode represents the most frequent category. For example, here, year 2010 has the highest count, so the mode is 2010. Note, however, R does not provide a built-in function for computing mode, so you must self-study how to write the mode function for different types of data. Sometimes a distribution may have two modes or multiple modes. Such distributions are called bimodal or multimodal respectively. Mode, although it shows the most frequent category, does not necessarily show where the majority of the distribution is centered. For example, in this last histogram, the majority of the distribution is located away from the mode. So mode does not represent a typical or the most common observation in this case. A popular measure of central tendency that shows the value around which a distribution is centered is the median. To calculate the median, we must first sequentially order the data, and the middle point of this ordered data is called the median. For example, consider this data that shows salaries in a small organization in thousands. If we order this data, the midpoint is 47, so the median salary is 47,000. However, in this instance, the midpoint was easy to find because there were 7 salaries and 7 is an odd number. If instead we have an even number of data points, such as is the case in the bottom example, then we have 2 data points in the middle, that is 45 and 50. So the median is now computed as the average of 45 and 50 and is 47.5. Essentially, median is defined as a value such that the quantity of data above and below it is equal. You can use this R code to compute the median. Another, and perhaps the most commonly used measure of central tendency, is called the mean. The mean computes the average value of the data points. So to compute the mean of the salaries, we must simply sum all the salaries and then divide the sum by the total number of data points, which in this case is 6. Note the mean is often represented by this funny looking U, which is actually a Greek letter called mu. Likewise, xi means the ith value of the data under consideration. Since we have 6 points, so I varies from 1 to 6. So in this case, the mean value is 64.17. Notice mean represents the average value, such as the average salary that the organization pays per employee. However, we have to be careful how we interpret this average because this average value is affected by some exceptional values or outliers. For example, in this salary data, 150 is the exceptional value, and it probably represents the boss's salary. So while the average salary paid per employee is indeed 64.17, nobody except the boss earns more than 60. So in the presence of such hugely influencing outliers, the median value of 47.5 better represents the center of the distribution. Because of this, it is often a good idea to report both the mean and the median of a distribution. Note, in a symmetric distribution, both the mean and the median are identical, but in skewed distributions they are different. You must study the left and right skewed distributions and compare their medians and means. We now discuss the statistical measures that tell how far out our data is spread. These are called measures of dispersion, and the first such measure is called range. Range is simply the difference between the smallest and the largest values in the dataset. For example, in the salaries data, the range is 150 minus 35, which is equal to 115. Here I also show the R code to compute the range. Note, range in R returns the two extremes of the data. And then the diff function can be used to compute the actual difference. As one can expect, the range is affected by outliers. The presence of just one extreme value, such as 150, can stretch the range significantly. Therefore, other measures of dispersion are needed. A better and a very popular measure is called interquartile range, or IQR. To understand that, we must first understand what are quartiles. To obtain quartiles, we must first sort the data into an ascending order. Now, the three quartiles are the values that split this sorted data into 4 equal parts, as is visible from the figure on your screens. First, we talk about the second quartile, or Q2, because it falls smack in the middle of the data and is the same as the median. The lower quartile, also called the first quartile, or Q1, is the median of the lower half. So it cuts the lower half into 2. Correspondingly, the upper quartile, also called the third quartile, or Q3, is the median of the upper half. And so it cuts the upper half into 2 parts. Note, the IQR, or the interquartile range, is the difference between the upper and the lower quartile. As we can see from the figure, the IQR represents the middle 50% of the data and therefore omits the extremes on both the upper and the lower sides of the data. Therefore, while a normal range that we discussed on the last slide is easily affected by extreme values, the IQR is not, as it represents the central data. The quantile function in R produces the quantiles. Here 25%, 50%, and 75% represent the lower, second, and the upper quartiles respectively, whereas 0% represents the 0th percentile, and that means 0% of scores are lower than this value. Essentially, that means it is the minimum value itself, whereas 100% is the 100th percentile, and this represents the largest value. Another useful command is summary, that gives the quantiles as well as the mean value. In R, we can visualize IQR with boxplots. For example, here we show the box plot of the prices column from the used cars data. The thick line in the middle of the rectangular box shows Q2, or the median, whereas Q1 and Q3 are the lower and upper sides respectively. The difference between Q3 and Q1 represents the IQR. Whiskers are drawn at 1.5 times the magnitude of IQR, above Q3 and below Q1. Any scores outside the whiskers are considered as outliers and are drawn as small circles. Because the extreme values are left as outliers, we can see that the IQR does not get affected by them, and instead IQR better represents the dispersion of data than the range. Much like the mean is the most popular measure of the central tendency, the standard deviation and variance are the most common measures of the dispersion. Standard deviation is in fact just the square root of variance. Hence, variance is the square of standard deviation. Since standard deviation is represented by the Greek letter sigma, variance of a statistical variable x is correspondingly represented by sigma squared. So variance is the sum of squared differences between the mean value mu of the data and each of the data points. So in this formula, the capital X represents the data variable under consideration, for example, the prices. The small x with subscript I represents each particular value of the variable in turn. Hence, I varies from 1 to n, where n is the total number of data points and mu is the mean value of x. In other words, it is the average of squared deviations from the mean value, that is variance. Since variance is a squared quantity, it squares the units associated with the data as well. So for example, if price is measured in dollars, then variance is measured in dollars squared. But when we take square root to get the standard deviation, we get the average deviation back in the original units. Standard deviation or variance can be computed in two different ways, and to understand that, we have to understand the concepts of population and sample in statistics. Suppose we want to create a distribution of the heights of all the European people. Then the population, or the statistical population as we call it, comprises of all the Europeans. However, since noting data about every single person in such a large population is very hard and perhaps practically impossible, in statistics we often try to make do with a smaller data set called a sample. The sample is drawn out carefully to reflect the properties of the population, and we shall study this in a later lecture on sampling and surveying. So now if we have to compute the standard deviation of a sample, we represent it with a small s and make two changes in the formula. First, we divide with n minus 1 instead of n, as we did on the last slide. And secondly, the mean value is now represented by x with a hyphen on top of it. We call it x bar. X bar is the mean value of the sample that we have collected. If instead we had access to the entire population's mean for some data set, then the formula for computing the standard deviation remains the same as that on the last page. Note, R provides a function SD to compute standard deviation. Note also that it computes a sample standard deviation. I've shown an example of the use of this function here and leave it as a personal exercise for you to verify that it indeed computes the sample standard deviation. The standard deviation indicates the spread of a distribution as a measure of dispersion should. So for example, if sigma or standard deviation equals 1, then the distribution is narrow. And this shows that most of the data is clustered together around the mean value. As the standard deviation increases to 1.5 or 3, we can clearly see that the distribution spreads out away from the mean or the central values. In normal distributions, it is very common to show how extreme or rare a particular data point is by looking at how many standard deviations it is away from the mean. For example, one standard deviation away either side of the mean contains 68.2% of the data points in a normal distribution. Similarly, if we extend even further to 2 standard deviations on either side, then that covers the 95% of all the data points. Therefore, the data points more than 2 standard deviations away from the mean are about 5%, the most extreme cases. So with that, we conclude this lecture. I hope you found it useful. I suggest you try out all the code and material discussed here and apply it to your own data sets, because you only learn by doing. I've also put the link to the used cars dataset below in the description of this video on YouTube. Goodbye, and see you in the next lecture.